Let's introduce this idea of chemical equilibrium. You can see here that we're going to have a couple of different topics here, but we're first going to start off by talking about what the equilibrium condition is and defining exactly how equilibrium is set. To help us do this, we're going to use this observation using this reaction equation. You see here on the left side of the equation, you got some NO2 and also some NO2. These are your reactants. By the way, yes, they're just the same substance, so why didn't they combine them together to have one coefficient? It's just basically showing that there's multiple particles here. And these substances are dark brown, right? So NO2 and NO2, those are collectively going to give you a dark brown color as a physical example. And then on the right side, the product here, you see that this guy is going to be colorless. So you shouldn't expect to see any color once you make a bunch of products. So we're going to start off again by using this this example by posing this question: when the reaction is complete, all right, when you think it's completely done, what color do you expect to have in the reaction vessel? All right, let's go and take a look at this diagram, this little picture here, and I'm going to kind of show us what's up. So I'm going to outline this. This is the tube, right? This little sort of pointy tube. That's got all NO2 at the beginning, right? So this is just NO2 only. And then you can kind of just make the reaction occur, and it's going to be allowed to happen, and then over some time you expect to be finished. And that's where we see this guy right here on the right side of that tube. Again, same tube, but in this case it's colorless. So you know that the contents of this is N2O4 only, right? There's nothing else in there. But here's the thing though, and this is where we have to be careful about this word complete. This word complete is only relevant for reactions that are only happening in one direction. It turns out this is not the case for this specific reaction. Now you might be wondering, okay, then if that's the case, then why do I have conditions here like this, and then why do I eventually have N2O4 in the end? That's because, you know, we as an observer here, or at least the person who did this anyway, kind of made some conditions change to make it look a lot more like it's colorless. So at the end of the day, let's kind of back up for a second. If I really did start with NO2, only reactants in this condition, and then I let it sit out for a while, the reality is that you wouldn't see ever this, right? You'd actually only see this as your diagram. So why is that, right? Even if you let it sit there for ages, the reaction will appear to have stopped at this color, where really some reactants remain and there are some products. Well, how do you know that some reactants remain? Well, it's kind of got some brown. But also, how do you know that some reactants are there? Well, it's because it's not as brown as it used to be, right? That means some of it went colorless, meaning it went to the right, or that there's some product in there. So this is actually what you would observe over a long period of time if this were allowed to just hang out undisturbed. Now again, some of you may be wondering, well, what's the point of this? Well, or how did they exactly get this? It's because we as an observer, or we as a scientist, did something else to it, which we'll talk about later on, to make it look like that. So it's kind of an artificial way to look at it. But really, at the end of the day, this middle picture illustrates what happens at equilibrium. So what's going on? This is again an illustration of dynamic chemical equilibrium, where we have a state where the concentrations of all reactants and all products remain constant over time. This means that there is a forward reaction going this way and a reverse reaction going that way that are occurring at the same rate. Right? So let's be clear about this. First of all, we're not saying that these are in the same amounts, right? We're not saying that they're equal amounts. That's not what equilibrium means. It's occurring at the same rate. So there is a forward reaction that's going at a certain rate. There's a reverse reaction that's occurring at a certain rate. Yes, related to the kinetics they may have just recently learned. However, the visual aspect of it, or even if you were trying to measure it, it would look like there's no reaction occurring. It looks very, very unchanged. And this reaction really never quite reaches completion ever entirely, because there's always going to be some amount of reverse reaction going on. Let's see how we look at this as a concentration over time. So this is a new reaction, different one here. You have H2O gas that's combined with CO. Your two products are H2 and CO2. So notice that, first of all, it is also, again, coefficients of 1 all the way across the board. So these are pretty much equal amounts of everything. And this would look different if you had different coefficients and stoichiometry involved. But anyway, what we have here is a reaction vessel. We just charge it with only H2O and CO, right? So just the reactants on the left side. Then they're allowed to react, right? Put them in a container, they're allowed to react. What would happen to the amounts of each? Right? So right now in this graph, I have time going across from left to right. My concentration here, initially, right, the amount of products in red, that's going to end up being nothing. Right? This red line represents the products. There's nothing at the beginning. There's no products that have been made. But what about my reactants? My reactants, again, here in green, I started with just CO and H2O, right? So I put that in there, and it's obviously on this would actually be two lines because one would be for CO, one would be for H2O. But because again they basically are on top of each other, we'll just treat it like that. So whatever value you get from this is going to correspond to CO and to H2O. Now this proceeds with time. You press start. It's going to start to consume this stuff, right? We're going to use up a lot of the CO and the H2O. Right, those stuff on the left side, but it's also going to produce some products as well. And as you can see here, sure it crosses lines, but eventually this one sort of levels out, flattens out. This one also sort of eventually levels out and flattens out. But at some point, specifically at this time right here in the reaction, both of the lines remain flat, right, meaning the concentration stays the same. So it stays the same. So it's going to take some while to get there, but that's effectively what it looks like as a concentration. Now, this next one right here is more about rate. So remember, rate is a concentration change per time, right? So in this case, we have, once again, the same reaction equation. We start with just H2O and CO. So we're just starting with reactants on this one. And then when you press start, we allow the substances to react and rearrange. So let's take a look at what happens in this diagram. First of all, time. Time, of course, is going from left to right, so we're increasing time. And then we have two rates we have to worry about. As you can see here, this is the forward rate. Right now, we're tying it to exactly one or two substances this time. We're saying that the reaction, the change in concentration, going from left to right, it decreases, right? Because you have lots of material, you start to use some of it up. You have less and less material as you go to the right. So the rate slows down quite a bit. On the other hand, at the very beginning, the rate going this way, going from left to right, or from right to left, going that way, that actually also starts to increase pretty quickly, at least relatively speaking, and then it once again starts to flatten out. But eventually, at this specific moment in time, these two reaction rates are going to be equal. If they weren't equal, you wouldn't have equilibrium, right? But the only way that we can have equilibrium is the forward and reverse reactions are at the same rate. So why, again, does it occur? Well, you have to remember, in our most primitive sense of what we learned so far, a lot of times we just tend to think of reactions always going that way, right? So when we react when these two bump into each other, like, separates or makes new products, and somehow it's like the reactants and products, they're almost like sequestered away from each other. When in fact, they're actually all colliding with each other. So this substance is bumping into this substance. Particles of H2 are also bumping into H2 and CO2, as they are being produced. Maybe not at the beginning because there isn't any there, but, as more and more of the products are produced, every single particle is bumping into each other. And so the question is, does it end up having a successful reaction as you bump into these particles? And according to this balanced equation, the only successful reactions or only successful collisions are going to be between H2O and CO to go forward. And in the reverse direction, H2 and CO2 can also make reactions happen that way. So some of these collisions, whatever they are, some of these collisions are going to be successful, but generally speaking for this one, the forward reaction and the reverse reactions occur because, those pairs are going to generate some kind of a reaction. Let's go and talk about this next thing called the equilibrium constant. This is going to be a big part of how we define equilibria. First of all, the law of mass action. This phrase, frankly, is really only used in this specific way, and I'm not exactly sure what the significance of law of mass action means, but I do know that this is going to be a representation of the relationship between the concentrations of reactants and products at equilibrium. Right? That's how it's underlined, and I'm also starring it. That very specific condition must be met. And it's going to end up being a mathematical expression. So we're going to use this generic math equation, right? This generic balance equation of substance A and B, producing C and D. And at the same time, C and D is going to produce A and B as a reverse reaction, and the corresponding coefficients, also lowercase letters. So we can calculate an equilibrium constant, capital K, using an equilibrium expression. Here we go. Equilibrium constant is K. That's equal to a fraction of C raised, and let me put this in brackets here, C to the Cth power times D to the Dth power divided by A to the little eighth power and B to the Bth power. And that's basically it, right? So if you notice, we have the concentrations of these in molarity, right, as the brackets with the C and D's inside these brackets, raised to their corresponding exponents, right? There's no inverse here to worry about. And, the coefficients, we can actually go and stick in the formula. There are some other situations we've seen in the past where the coefficients don't exactly get used as directly as it appears. So this is nice. We get to do that. But also notice this is generally always going to be some combination or some expression of the products over the reactants. I'm not doing a pretty bad job of that. Let's reactants. So whatever the case, anytime you calculate K, you should always think of it as products over reactants. Now, why exactly products over reactants, I frankly don't know. But do know that the result of this law of max action, this application of it anyway, gives you these mathematical expressions. Right? So this is going to be key to apply what we have here. Also notice you have some key terms here. Equilibrium constant, that's K, that's this guy right here. And equilibrium expression is going to be looking like this. And of course, depending on the reaction, you have different labels inside of it, different exponents, but altogether this will be called your equilibrium expression. Let's go and take a look at some examples. The equilibrium expression for the following equilibria. The first one right here, N2 plus 3H2 gas. That's an equilibrium with 2 NH3. All right, so that means to calculate this, I'm going to go and start off with K. K is equal to NH3, right? That's products over reactants, so the product is NH3. That's the concentration of it, and we're going to square it, divided by N2 times H2 to the third power. There we go. That's it. So products over reactants, that's your equilibrium expression for that equilibrium. All right, what about this guy right here at the bottom? So here we go. K is equal to N2O4 raised to the first power, coefficient of 1, divided by NO2's concentration. That's supposed to be a 2. Let's get rid of that. And that's going to be squared, just like that. Now, this idea about the equilibrium constant, first of all, this value is actually going to be affected by the temperature, but never by differing concentrations, which we'll talk about in the next slide in a little bit. All right, it's only affected by the temperature, not by differing concentrations. You probably can think of a thing or two that's only affected by temperature, but not by the different concentrations. There's no units, right? Even though there's obviously a bunch of numbers that get plugged in with the appropriate concentrations, and they're being raised to whatever exponents, but you never should include units. And finally here, there are some equilibrium constants of a wide variety of contexts, right? So you have the K that we just talked about, but you also have generically KEQ. By the way, these two are more or less equivalent to each other. But then you also have some other ones. You have KC, KP, KSP, KA, KB, and this is only a handful of the ones that you could really see in introductory chemistry. I will say that we're pretty much only going to focus on these 4 right here, and we'll talk about what they mean in just a little bit. But for now, though, just know that there's a variety of them, and we'll get to those in a little bit. First of all, let's go ahead and see how we can calculate equilibrium constants. So this is a little data table here that's given to you. You've got 4 different experiments, right? And what they're saying, if you look at this carefully, is that you got the concentration of N2O4, and you see a little I right there. You have NO2, which is also I. So I'm going to do a little imaginary dash line to make it now more imaginary, or a little bit less imaginary. And what I'm doing here is showing you that these, again, are I's. This one right here is EQ, and this substance at EQ. And you can probably imagine that means that EQ, right? That means that those are the concentrations of your substances at equilibrium. Whereas, if you have a little I right here, that's basically short for initial. So these are your concentrations of your substances initially in the container. And then, at equilibrium, you see right here, those are the values that are provided for those 2 substances. And so, the question is asking you to calculate the equilibrium constant for each experiment below. All right, let's see what that's going to look like. So, to calculate it, right, remember you're going to have to start with your equilibrium expression. That's going to be products over reactants. It's going to be N2O4 raised to the first power over NO2 squared. And so at this point, we're just going to plug some numbers in. So let's go ahead and do it for each experiment. Let's start with experiment number 1. To make that happen, we go ahead and say, okay, K, I got to solve for that equilibrium constant, K, divided by, or is equal to NO2 concentration divided by NO2 squared, or N2O4 divided by NO2 squared. Make sure you look at the right chart. A lot of times they'll give you this stuff right here. Somebody will be like, oh, I plugged this in, I plugged in some zeros. How is that possible? It's not going to work out. Yeah, it's because you're plugging in the wrong chart. Look at the one on the right, EQ. Now, to make this happen, plug some numbers in. N2O4 on top. Let's go and look at experiment 1. That's going to be 0.00140 molar. All right, that's all raised to no power. And then over NO2 at that equilibrium 0.0172 molar squared. And then basically do some math. Plug your numbers in the calculator and make sure you follow significant figures. The result of this should end up being 4.73. That's it. Let's do the same thing for experiment 2. Experiment 2, once more, you have experiment 2. You have that same mathematical expression you can apply, right? It's an equilibrium expression and applies to this one equation. So you can use this multiple times. And that's going to look like this for experiment 2. 0.00280 molar divided by 0.0243 molar squared. Plug some numbers in, and you should get a value of 4.74. Okay, so let's talk about this for a moment here. You do know that this is going to end up being slightly different, right? So it's a constant, it's supposed to be the same, but that's, what you expect with some variance, and that's okay. The next thing is too, though, is that they are pretty close, right? This is actually supposed to be a value that is going to change, it doesn't change. And even though you put in different amounts, right, plug in two completely different amounts as your equilibrium concentrations, that doesn't matter because it should still give you the same equilibrium constant. That's the whole point of the work. Let's go ahead and wrap it up by talking about these ideas here. So let's talk about this idea of equilibrium position. This is basically a set of equilibrium concentrations, right? That's it. All right. So whatever substances you have, if it's at equilibrium, those concentrations are your equilibrium position. Right? So that's a very specific term there. An equilibrium reaction can only have one equilibrium constant. Like we just calculated from before, the equilibrium constant is 4.74. Right? You could also then say 4.73, so on and so forth. Yeah, that's fine. All right, let's just say it's 4.74 for now. So it's going to have one equilibrium constant. If you change a reaction, you're going to have a different equilibrium constant. However, an equilibrium reaction can have an infinite set of equilibrium positions. Of those infinite, I'm giving you 4 different ones, right? So this is one set of equilibrium conditions. These values right here, these concentrations, is a second one, a third one, fourth one of equilibrium positions. Finally, let's talk about this last bit here, variations on the equilibrium constant. Let's see if we can kind of compare what's going on here. What's the value of Kc of the second reaction? By the way, Kc, this is supposed to represent K of an concentration, K by concentration. It's a minor detail, which we'll get to in just a little bit, but in another later time anyway. Write the equilibrium expressions for both reactions to help us out. All right, first of all, we have this reaction given to us right here. This is going to be what is provided, so the K of that one is going to be equal to NO2 squared over N2O4, right? That's the K for this guy, right? That's also equal to 0.212. But what if you can see right here, the reactions flip. The reaction and products reactants and products are flipped on either side of the equation. Let's see what happens, right? So the result of that is going to be N2O4 over NO2 squared. All right, well, how does that help me out? How does that help me solve for this? I literally just wrote 2 different expressions, neither of which have numbers to it. But don't forget, right, first of all, when you look at these two, they're basically upside downs of each other. They're flipped, right? So this value right here is basically the reciprocal of that. What does that mean about this? Well, if that's the case, then I know the value of this is basically the same thing as 1 over 0.212, right? Isn't that basically what this number is? So 0.212 divided into this 1, that's going to equal, well, surprise, 4.72, right? Same reaction as we saw before. So if ever you switch or flip the reaction, the value of K is applied where it's the reciprocal. This is going to be a little bit more involved, but I think it's still something worth doing. What do we do about the second reaction's Kc? What's the goal here? How do we get that value? All right, let's go and start off what we normally do. We go ahead and take Kc, or K, let's do K for the sake of simplicity. You got NO2 squared divided by N2O4, just like that. This one down here, that's going to be NO2, that's an N, to the 4th power divided by N2O4 squared. Okay, well, what's up with this guy? Well, if you notice, right, these are not exactly the same thing. But if I rewrote this guy, all right, again, knowing that NO2 on top, N2O4 on the bottom, I can rewrite this to make it look a little bit closer to what I have originally by doing that, divided by N2O4. Right, and then this whole thing is squared, isn't it? Right. Isn't that basically the same thing, just rewriting it to make it match a little bit more closely to this? So if I know that NO2 squared, right, over N2O4, this term right here, this whole thing, that's equal to 0.212 squared. Can I just plug that in there? So then that gives you a value of 0.0449. So that's the Kc, or the equilibrium constant for this second equation, which is just the doubling of the coefficients. Right. So you see here, right, doubling the coefficients, you square the exponent there, right? You put it and make it 2. What happens if you were to triple it, right? What happens if it was 3 N2O4 in equilibrium with 6 NO2? What might you think would happen there? Feel free to give that a go, but that basically takes care of it. All right, that'll do it.